Hey everyone, Max Schneider here, and I am looking to give you guys a overview on distributed generation with kind of an introduction to the U.S. electrical grid and how distributed generation is going to change that. So, as a brief introduction to give you guys kind of a vague idea of this, in the modern day, there's a lot of drivers or pressures and trends, you might call them, that are motivating the end users of electricity, like residential users and industrial and commercial folks, to generate their own power. Um, Four of those big drivers are the economics, which refers to how the technology to generate your own power is cheaper than ever as economies of scale and developing manufacturing processes drive down the prices of technology that were once pretty expensive. Second is the technology itself has improved a lot. It isn't just cheaper, but it's also more efficient. There's more sophisticated energy storage that can couple with it to make it function more effectively. And then there's even better integration with the existing system, and that's also improving over time. All of those things are. Um, from an environmental aspect, as the third thing, people are kind of taking environmental action into their own hands, assuming they can afford it, and just bypassing the entire sort of fossil fuel dependent electricity generation system that many governments and the world is trying to overhaul, and they just make their own clean energy. Um, and finally, regulatory incentives are strong. Kind of tied in with that last point, governments are trying to help the environment. And so regulations are often encouraging more renewable energy adoption, either on a utility scale or a residential scale. In the utility sense, it usually ends up with more smaller producing generation facilities that are closer to the end users. And with residential generation, it's right there. And I'll be concentrating on solar for a lot of this, just as kind of a disclaimer, just because wind is not very common. Other technologies are not very common. Solar just by far dominates residential generation and distributed generation. Um, anyway, these drivers come together to produce these trends that are really changing the landscape of our entire electrical grid, which has serious consequences. And without intentional changes to accommodate these trends, these adoptions in solar and smaller generation facilities, a system that was designed for one purpose will be used for another and could end in disaster. So the U.S. electrical system, uh, by and large, is divided into three huge interconnections. There is the Western interconnection, the Eastern interconnection, and of course, Texas has its own interconnection. These are the largest, uh, I guess, hierarchies of electrical organization or management. Within each of these interconnections, there are smaller regional operators that might span a couple states or even just parts of one state. Um, but within the interconnections and between those regional operators, there is a large degree of sharing of power. So, power that is generated in Washington state is shared with California and New Mexico and Nevada and Arizona. But rarely does power cross these interconnections. There are a couple discrete points, but for the sake of preserving the generated frequency of the power, we'll get more into detail about why frequency matters in terms of power quality, but it's really difficult to synchronize these huge three interconnections together and keep the quality of the power high. And just as a couple stats, from 2016, the US grid had over 7,000 power plants, 160,000 miles of transmission lines. Transmission lines officially are considered any transportation cable for electricity that's over 60,000 60 kilovolts. Excuse me. Um, there's many, many millions of electrical distribution lines that are under 60 kilovolts. Those kind of like fragment from the graph or the map, on the right. That's just transmission infrastructure, and it's probably a pretty dated map. But you can see how tangled of a web it is. Each of those, as it gets close to a city, kind of fractures into thousands of distribution lines. And all of that power is getting transported to about 145 million electrical customers, the end users, whether industrial or commercial or residential. So our grid was not necessarily this. I guess it's a misleading way to start this slide. There wasn't a master plan for our grid before it was made. It kind of was designed as it happened, but it was limited by the technology of the time. So around the late 1800s, when electricity was new and Thomas Edison was putting in his Pearl Street station in 1882, that place only lasted 8 years, it was expensive. It was really expensive to build these power plants. It was new technology, like all new technology is, and so rich people could build like one, and then they would output a bunch of power to the area. These were called point source generators, you could call them, and the power would flow outward from the point source generator. At that point, the power was transported to customers by transmission infrastructure. Usually, as it got more into the modern era, this meant it passed through a step-up transformer to go to a transformer voltage between 60 and 750 kilovolts. After it's traveled a long distance, it gets stepped down to more of a distribution voltage between 120 and 60 kilovolts, and then it gets passed to the end user. But this power flow was always very linear. It went from source to load, and there were a few rare exceptions that there might be a small backflow or nuances, but by and large, the grid was made to follow this source to load model. And then the electronics and the hardware in between, those transmission infrastructure and the generation facility, keep things functioning and usually serve as a check, kind of like one-way gates so that the power can flow out towards the load but not back towards the source. They do the stepping up and the stepping down of the voltage, and they have relays for remote control of the grid to manipulate the flow of power, breakers to act as protection measures in case there's too much energy on a system. And then there's lots and lots of monitoring technology. As the grid has gotten more modern, monitoring technology for real-time metrics of what is going on in the grid have become more and more and more important. And it's still not enough. And finally, the generation of that original point source had to match the demand plus the losses incurred along the transmission system at any given moment. It was an instantaneous one-to-one generation, had to match the load. So that's part of the reason those monitoring technologies were so important, and metering of electricity is so important, because there's no storage on the grid, and so the power has to be used as it's consumed or consumed as it's used. You pick. So before we continue, I want to cover what constitutes power quality. What is good power? Is not all electricity the same? And no, the answer is not all power, especially electric power, I guess I should say, is the same. And the way that you would check the quality of your power is by analyzing the waveform. On the right, you can see kind of a typical sinusoidal waveform that would more or less be what you read coming out of your outlet at home, oscillating between positive and negative 120 volts. But the quality of your power is typically shown by the stability of it along a few different dimensions. And the first is, like I mentioned, voltage. So you want to maintain a consistent voltage of technically what comes out of your power outlet if you take a different voltage metric, because it's changing all the time, right? It's oscillating between positive 120 and negative 120 volts over and over. That would be like an RMS voltage of like 110, I can't remember. But it's not static, it's not a direct current waveform. Um, After keeping the voltage consistent, the other main thing utilities try to do is keep the frequency consistent. And as shown right, the time it takes for a waveform to repeat is known as its period. And if you invert the period, do 1 divided by the period, you get its frequency, measured in hertz, or cycles per second. And in North America, our power is 60 hertz. In Europe and just about everywhere else in the world, big surprise, it's not 60, it's 50 hertz, but we're close. And another major job of utilities and all of the controls and hardware they have on the network is to keep frequency between like 59.98 and 60.02 hertz. And finally, I got to change the graph here to depict this final one, but the phase of your power matters a lot. This one's a little bit more nuanced and complicated, but suffice to say that as power is generated, it's generated on AC synchronous generators, where essentially 3 of those sinusoidal waveforms are generated at the same time. They're just out of phase by 120 degrees. So the phase refers to kind of like the delay between these waveforms. And if waveforms are out of phase, they can interfere with one another, or they can disrupt the technology that is on the network, on the grid, or that the end user has. And bad quality power can actually damage equipment. It can create safety concerns for anybody nearby. It's bad. But lucky for us in America, we have very high quality power, very consistent power along those 3 dimensions. So given that sort of intro to our grid and what power quality looks like, how is our grid today changing? As I said earlier, in 2016 there were over 7,000 power plants in the US, and this graph to the right is from the Energy Information Administration, the EIA of the US. It's like an awesome information source for anything energy, really, in the world, but also especially in the US. You can see that 2016 lands really close to the end of the graph there. It's about 3/4 of the way between the year 2000 and the very end, and things are topping out at about 4,000 billion kilowatt hours, and they don't change that much. Pretty much after 2010, it doesn't change that much. But also, information from the EIA states that as of December 31st, 2021, so pretty much the beginning of 2022, there were almost 12,000 power plants, each one being above 1 megawatt. That's kind of like the cutoff for these being considered power plants. But the power didn't go up. So what's the deal here? And this kind of points to the conclusion, or the point I'm trying to make, which is that generation is distributing. There's more generators, but it's the same amount of power. Therefore, that generation potential is being spread out and in smaller bite-sized amounts. Additionally, our grid is changing in another way, in that residential solar is getting more and more popular. And actually, in the last 6 years, it really has exploded. It's gone way up. Looking at the graph to the right along the same time scale from 2016 to about beginning of 2022, residential solar installations in the US more than tripled. And that's huge. That is a lot of little tiny generators on the grids, and not all of them are grid connected either, so this might not be the most accurate metric for judging that, but many of them are, because people want to take advantage of selling power back to the utility, known as net metering. And you can do that at different times in the day based on the price of power, or just when power is in excess to you or in surplus. But alongside residential solar explosion here is also a major increase in utility and commercial solar, especially utility, but commercial's gone through a big growth. You can see kind of a similar magnitude of increase when you look at all of the solar installations in the US. over a tripling of solar installations, and this is a huge, huge distribution of generation. As I said previously, these are both major things pointing to the fact that generation is becoming distributed whether or not we like to or not, or whether we want it to or not, excuse me. So the smart choice would probably be to prepare for it or start accommodating that change instead of fighting it. So I keep kind of dancing around it, but I haven't explicitly defined it yet. I think it's time to give you guys a definition of what distributed generation is. And according to this guy, Lucian Iona Dulau, he's a Romanian holder of a PhD. He's from a technological university in Romania. To him, it is the generation of electricity closer to the load. And I really liked this definition. It's deceptively simple because it contains just about everything I've talked about. It really does boil down to generating your power closer to where it's going to be used, which in the end should be more efficient, right? You're not transporting over all of those miles of cable, incurring all those losses. And this can kind of happen along two ways. If we start with our original model of the point source generator and then kind of a municipality nearby, the power is exported from the point source to the municipality. But distributed generation occurs when that generation facility is kind of broken up into smaller things, smaller power plants, you could say. Maybe one is a solar plant, another's a wind farm, another's a traditional coal plant or like a peaker, a natural gas peaker. And then it also happens via the adoption of residential generation. Or it doesn't have to be residential. These little houses could also be like factories or office buildings. When these end users put generation potential on their own building instead of just relying on smaller nearby generators. So we know distributed generation is happening. We know kind of what it looks like. And we know a little bit more about how our grid was made. What does all of this mean? What does distributed generation ultimately mean for our grid and for our system that we have? And so my two primary sources for going through this analysis was a paper out of the journal known as Science called The Effects of Distributed Generation on Electric Power Systems. A little bit on the nose if you ask me. That guy quoted as the main author. And then I also interviewed one of my oldest friends who actually is an electrical engineer working for the Franklin County PUD as a system engineer. He's working on his professional engineering certificate right now. He's, in the thick of this industry. He literally works with people installing solar on their homes and industrial customers trying to get their own generation potential going. And to break things down to kind of a high level before I get into the weeds a little more, I'll just give you guys a pros and cons chart. On the positive side, distributed generation creates a system that is more resilient, right? Instead of having the generation potential of thousands of homes in one spot, you have it distributed over a larger area. So if some enemies to the state were to try and knock out our energy infrastructure, they would have to attack a bunch of several points instead of just one big power plant. Distributed generation is kind of a natural force to incorporate renewables. It usually favors smaller generators, and renewables typically are smaller generation potential. And so the two go hand in hand, and it's driving that trend further. And then on top of all that, it saves people money. If you can afford to get your own home generation potential and stay in the home for decades, you eventually get a return on your investment, and then you can start selling power back to the grid for a profit and completely eliminating your electricity expenses. However, on the downside, distributed generation results in significantly increased complexity of the grid. That's hard. That's expensive, first of all, for utilities to manage, but it's also difficult and can result in decreased power quality during that transitionary period we're kind of in, where we're figuring out how to go about handling distributed generation best. And kind of like I mentioned in the first point, this takes a huge amount of investment, so it's going to cost money, and the money usually comes from us, the taxpayers, because this is public infrastructure. So now I'm going to dive into the weeds a bit about why distributed generation causes these problems. I'm not going to go into like equations or calculations. I'm just going to give you guys a few points and then give you ways to kind of bend those effects more broadly. Starting with the first one, distributed generation changes how utilities operate and control the grid because people are in charge of their own generation, so they can turn it on or off when they want. Granted, there's a standard for power that is put onto the grid. People have to meet certain, frequency, voltage, and phase requirements so that it's not disrupting too much. But those on and off cycles that the utility is not in charge of still affect things. That means that the utility has to invest in more monitoring and more controls to see when, what the state of the system is at any given moment. Additionally, if one of these distributed generation systems, someone's home, it has a problem with the equipment, it'll trip a breaker, and it can island, that's what the term is, but isolate the distributed generation home from the rest of the grid so they no longer have a power source, a bigger power source to tap into. The next one, short circuit levels are increased. So short circuit levels is kind of referring to the amount of power at any given moment on the grid, the amount of energy that is being transferred through these wires. And if a short circuit occurs, where a huge amount of energy now has a low resistance pathway to travel across, with a greater amount of energy in the system, it's now more dangerous because we're adding more power closer to the load. As my friend Jacob put it, there's more power moving around, and if something happens, the hardware and the personnel that are working on the system are at a higher risk. The third one, load losses change. Before, with the point source model, there was a great distance between the generator and the end user. And now that distance has decreased, which decreases essentially the resistance of the system. Those are losses incurred as electricity travels to the load, or load losses. Jacob mentioned that utilities use the concept of something known as electrical miles, which is like a measure of how hard the energy has to work to the load. You could just think of it as the net amount of resistance it encounters, or just as another way to think about losses. But adding these generators close to the load changes all of that. Voltage profiles change along the network. So before, in our fourth slide, I showed you guys how there's more or less a linear path from the generator to the load. Obviously, it's not that simple, but that's a good way of thinking about it. That's no longer the case because power and voltage is being injected into the system at the end, close to the user. It's changing that voltage profile. Instead of it being like a steady decline, you might see it increase at certain points, and that requires greater monitoring and control from the utility. Again, you might see a theme here with what I'm saying. And that can be pretty expensive to incorporate. Voltage transient will appear. So this is something that happens when you turn on or off, like your inverter, as you try and sell power to the grid. There's a small amount of transient energy that is propagating through the system, and that can require some compensation. Typically, it's fine, though. When I asked my engineer friend Jacob about this, he said that voltage transience typically refers to how inverter-based systems cannot produce a smooth waveform. So to put that more simply, when you generate power at one of these big facilities, one of the big traditional power plants, they use huge synchronous AC generators that create a really smooth three-phase waveform. But if you generate it from a battery, say in a solar installation, and you have to digitally create an AC current, that happens with little tiny micro steps. that sort of look like a smooth waveform, but if you zoom in, it's really jagged. It's flat, it's DC, and then they bump it up, and then it's flat, and then they bump it up, and it kind of creates a waveform that looks like AC. That's very jittery, those little bumps in that generated waveform, and that can create voltage transients, which requires greater, you guessed it, monitoring and control from the utility. Congestions can appear in system branches. This is more or less just like equipment has a rated current that can go through it. And if you surpass it, then you melt the equipment. You destroy the equipment. And because people are switching on and off their system to push power onto the grid, the utility needs to know when that's happening, and they need greater monitoring and control to accommodate that. But it also manifests in an interesting way. Jacob was telling me that typically in public utilities, growth pays for growth. And that just means that when, say, a big industrial customer comes in and they want to build facilities in your area, the area is growing, they pay for additional electrical infrastructure that is needed to support them. So it might be that someone moves in, they pay for power, someone moves next to them, and they can keep using the power that was built, but a third person comes in and they sort of overflow the capacity of the system. They now have the burden for paying for the upgrades to the system so that it can handle all of the customers. In residential solar, that's not the case. When you buy a solar system, or a solar power system for generating electricity, you aren't expecting to have to upgrade the utility to handle your system. That's not what you do. So who pays for it when the last customer to add solar to their house is overfilling or overloading the local distribution infrastructure? That falls to the utility, and that's expensive. Power quality and reliability might be affected. This is kind of the consequence of all the things above it, like voltage transients, voltage profiles, load losses changing. So power and quality are based on kind of the old model of our grid, going straight from point source to load. And these changes affect the ability of utilities to manage and control that power on the grid. And they're still kind of learning how best to go about it. So in this transitionary time where there's distributed generation growing, power quality and reliability will be affected, like it'll be decreased sometimes. Finally, network protections might not function properly. This is similar to power quality, just that there are pieces of equipment on the network designed to have the load behind them, to have the source of generation behind them and the load in front of them. And when you start putting generation sources by the load, there's now generation sources behind and in front of these protection equipments, and that drastically changes how they would function. And if you don't have functioning network protections, the grid can burn itself down or blow itself up. So that was a lot of specific stuff. And if you want a kind of better way of thinking about each of those points I covered, I sort of bin them into the three characteristics of complexity, reliability, and safety. Starting with complexity, changing how the grid operates and how you have to manage, control, and monitor it, that's always going to increase complexity. The last two there are kind of like consequences of the first six. So that's all increases in complexity, trying to figure out how to handle those things. Moving on to reliability, short circuit levels increasing is not as much of a reliability issue, and voltage profiles changing, all that. Those are just like facts of how things will change. If load losses are changing, that can change how the grid is trying to operate things, make it less reliable. And network protections not functioning is really more of the last one, safety. And I think that covers the first two as well. Changing operation and control. So if the utility is using new processes, there's risk in doing things differently, and people have to learn how to do them right. So there's going to be mistakes at the beginning, kind of like when the fresh batch of newly minted doctors comes out every summer, and like hospitals are full of doctors that don't know how to do stuff. Um, anyway, that's how I like to think about these. So, what kind of conclusions can you draw from this? Truly, I just wanted to write this down because I always try to incorporate something for people to take home with them at the end of my presentations. There's nothing to take home here other than the grid is changing. You don't have to do anything. There's no call to action. But know that the utilities in our country are working really, really hard to accommodate these changes. Because there's potential for injury, there's serious risks if things fail. If people don't have heating in the winter or cooling in the summer, people can die. So there's big risks involved with not acting, but also if we really lean into it, there's a huge potential for making a better grid that is more environmentally friendly and more resilient. But everybody's still learning how to do this best. And in my opinion, there's opportunity and ambiguity. Before the rules are all set in stone and everybody knows the most optimal way of doing it, find ways to game the system a bit. Get your solar system installed and double dip on those incentives, you know? Things like that. Anyway, that's it from me. I'll give you guys a shot of the references slide and the